Welcome back, ladies and gentlemen. Today we're going to tackle section 12.3, the surface area of pyramids. Up on the screen you'll see your exit question for the day. To start off with, I want to consider this pentagonal pyramid that is pictured at the left. You'll notice a new variable being labeled there, a cursive L or a script L. And that script L is going to stand for something called slant height, or the height of one of the sides of, or one of the faces of the side of the pyramid. So new letter and new vocab word for you. Probably the best definition of each is just this picture, so you might as well copy it down. But I want to consider how to find the surface area of that pyramid, including all of its faces, including the base. So as I hinted before in the previous lesson, the best way to do this, I think, is to draw a net. And if you draw the net of that pentagonal pyramid, you get a star shape, which is kind of cool. And I've kind of unfolded it in such a way and then labeled everything as is. You can see you've got an apothem length here, and then you've got the slant length there, and that's a right angle. So you can see the surface area of this pyramid is actually divided up into 6 different shapes. A pentagon, so the area of a pentagon, and then the area of 5 triangles. So if we were to try to find the surface area of it, we'd have to find the area of the base and add it to the surface area, or the area of 5 triangles. The area of the base is a half times apothem times perimeter, so we can take care of that. And then the 5 triangles each have 1/2 base times height. So I have 5 times 1/2 times base times the slant height of the original pyramid. Now, if you take and combine that 5, remember multiplication can happen in any order, but if you take that 5 times the length of B, so if we have B here times 5, we have 1, 2, 3, 4, 5 B's, and that would be a complete perimeter. So the overall surface area for this particular pyramid would be 0.5 perimeter times the slant height plus the area of the base. And it just so happens that however many sides the base has, that's how many triangles will form the pyramid up on top. So no matter how many sides the base has, you will always have basically 1/2 times the perimeter times the slant height, no matter, again, how many sides the base has. And that's your theorem for the day. Theorem 12.4 gives you a formula. The surface area of any pyramid is the area of the base plus 1/2 times the perimeter times the slant height. And it is separated into 2 terms, one being the area of the base and one being the area of the lateral area. So if you're asked for just the lateral surface area, you only do calculate that term right there. Next up is a special sort of pyramid, one with a circular base. We call it a cone, and it can also be described with a slant length. And the idea is to try to figure out the surface area of that. And drawing the net of a cone is not an easy task. Why don't you pause the video and see if you can take a guess as what the net of a cone would be. If you've done that correctly, it looks like this. And basically the net of a cone is a circle and a sector. Now, to find the total surface area of this cone, there are 2 basic shapes that we need to find the surface area of, or the area of. One is the circular base, which is no problem, pi r squared for that little guy. The second issue would be the area of the sector. And the area of the sector gets a little bit more complicated because there's no defined angle. However, there is a relationship between the slant height and the partial circumference of the larger blue circle, in that the partial circumference of the blue circle is the entire circumference of the small circle. So we're going to use that information to our advantage here. So if we were to try to figure out the surface area of the cone, it would be the area of the base plus the area of the sector. And to find the area of the sector, we can set up one of those proportion equations where we know that the area of this blue sector shares the same proportion as a partial circumference, or an arc, versus the entire circumference. So we can write up a proportion equation just like that, just like we did in the previous chapter. And if we start plugging in stuff we don't know the area of the sector, but the area of the entire blue circle, if it were closed up, would have that as a radius, so that times, or that squared times pi. The arc length would be 2 pi r, because it is the circumference of the smaller circle, and the circumference of the blue circle would be 2 pi l, because it has a little bit larger radius than 2 pi r. So now we have everything in that formula except for we got a couple script L's in there and whatnot, but we can simplify this as much as possible. So I'm going to bring this term over here by multiplying by pi L squared. And the result of that looks like this. And then a little simplifying is in order. Just cancel a few things out. One of the script L's cancel, 2 pi's cancel, and then 2 2's cancel. And if you just rearrange everything so it looks a little bit nicer, you get the area of the sector is r times pi times the slant height, which means all we have to do is take that term and substitute it in for that little guy right there. So you get the surface area of a cone is the area of the base, which is pi r squared, plus pi rl, the area of the sector that is dependent on slant height. And that's theorem 12.5. There it is in two different forms, the area of the base plus the circumference times the slant length, or pi r squared plus pi rl, whichever you prefer. And you'll also notice this little guy right here is separated up into two segments, one that describes the lateral surface area and one that describes the surface area of the base. All right, I'd like to do two examples today, both of which are asking for exact answers. So first one is find the exact surface area of that entire pyramid. All right, to do this, we're just going to use the theorem, use the formula from the theorem. So I'm going to write that down and see what I can figure out. So I need the area of the base, which is a regular hexagon, and then I need the perimeter of this hexagon too. And you'll notice that no edge of this hexagon is labeled, and I need the slant length or slant height, which is labeled. So I have one dimension here. I'm given that this is a regular hexagon. Actually, it doesn't say that, but I'm going to say that it is. And then we have to figure everything else out. So the area of the base is going to be 1/2 apothem times their perimeter, and from there we really need to get on towards that perimeter, and the apothem is labeled for us. That's nice, but we really just need the side length here. Now this is a hexagon, so it has 6 sides. You divide 360 by 6 and you get 60 degrees. So 60 degrees in the larger triangle here, which means the smaller triangle here has a little sliver of 30 degrees. And all of a sudden you've got a 30, 60, 90 triangle where the long side is 5 times the square root of 3. So you divide by the square root of 3 to get this side right here. And that ends up being 5 feet. And that is 1/12 of the way around the whole perimeter. So multiply that by 12 and you'll get 60. So I take and I put in all the numbers that I know, 0.5 times the apothem length times the perimeter, which is 60. That's 5 times 12, plus 0.5 times the perimeter again times the slant length. And then from there, it's just a matter of combining what you can and what you can't. So in this term, we have a radical 3 that will not combine with anything over in this term. So that kind of creates two unlike terms, but everything outside the radical can be combined. So 0.5 times 5 times 60, and all these numbers are just multiplied together too. And if you do that multiplication, you get 150 times the square root of 3, and over on this side you get 420. So you have to leave it like that and throw a label on it. Very ugly answer, but that's the way it is. Next up, I'd like you to find the lateral surface area of this cone. Pause the video and see if you can handle this one. To get started on this problem, start by just writing down the formula for the surface area of a cone and see what we need to find. So we know what pi is. It does not look like we have a radius labeled. We know what pi is again. We don't have a radius again, and we need a slant length, which is labeled. So we have slant length, and that's it. But we also are noted that we only want lateral surface area. So we only want this term, the cone part of the cone, not the circular part of the cone. So we only have to deal with this part. So we really only need to find a radius. And you'll notice that they give us a degree measurement, and you've got a 45, 45, 90 triangle. So we're going to use our special properties or special triangle properties, which basically says that there is a 1 to square root of 2 ratio going from short leg to hypotenuse. So we have to divide by the square root of 2 to get this length, which is also our radius down there. Doing that, we have to rationalize the denominator, so we'd multiply by square root of 2 over square root of 2, and then combine everything and simplify, and you'll get 3 times the square root of 2 is our radius. And then we can go ahead and pop that into our formula just like that. Combine all the numbers on the outside of the radical together. The pi, the 3, and the 6 can all basically be multiplied together, or at least crammed up next to each other to show that they're being multiplied, but the radical needs to stay inside the radical. So we take 3 times 6 to get 18, and 18 pi times the square root of 2 meters squared. Again, an ugly answer, but that's an exact answer format. There's your homework for the day. I'll see you next time.